Alright students, today we're going to look at this particular problem. Actually, we've got two problems dealing with friction. They're a little bit more advanced, that's okay. So in this case we have a 5 kilogram steel crate, and it's being pulled across a steel loading dock with a rope that forms a 30-degree angle with the horizontal. Does the crate move when pushed with a force of 20 newtons, 30 newtons, 40 newtons, 50, 60, and 70? So fundamentally the question is, are we going to be able to overcome the static friction force? And in class we looked at an example where you were pulling it horizontally. Now we're going to be pulling this crate with a rope at an angle of 30 degrees, and we're going to see how that actually affects the normal force. If you remember, something that we mentioned is that if you pull angled up a little bit, that's actually going to relieve a little bit of the weight force, so to speak. The normal force is going to be a little bit lower, and so that's going to affect the friction that is involved. So let's go ahead and draw ourselves a free body diagram. We've got weight going down, normal force going up. We're assuming that we're pulling this object to the right, so friction is going to be to the left, and our force or the tension on the rope is over there up and to the right. Now what we have to do is resolve that force into its two components, the x component and the y component. So our trigonometry tells us that's just going to be f cosine theta and f sine theta respectively. Now we'll write our Newton's second law. So summation of forces in the x direction is everything to the right is positive, so f cosine theta, and then everything to the left is negative, so minus f, equals the mass times acceleration in the x direction. And then we'll go ahead and write the, something else to note. What we're fundamentally concerned with is what is the relationship between f cosine theta, the force that we're pulling horizontally, and the friction force, specifically the static friction force maximum, or the maximum static friction force, because we want to know, is this right here, the x component of this tension, is that going to overcome Fs max? If it doesn't, then our crate is just going to sit here on the loading dock. If we are able to pull with a greater force than the static friction force maximum, then it'll start moving, and that'll be great. But that's fundamentally what we're wanting to compare. Before we can figure out this, we have to write Newton's second law to find the normal force. So summation of forces in the y direction, see everything that's going up is positive, so normal is positive, f sine theta is positive, weight is negative, it's going down, that equals mass times acceleration in the y direction. Of course, since our object is not accelerating up or down, that value is 0, which is awesome. We can solve this for the normal force. It is equal to the weight minus f sine theta, just bringing those to the other side. And then the weight, we remember, is equal to the mass times gravity. So if we actually throw in the numbers there, we have 5 times 9.8 minus 20 sine 30 degrees. And I think I make a typo right here, so you just have to bear with me. It's 39. I'm not sure if that's actually correct. I'll change that here in a minute. So keeping that in mind, Fs max is, the formula is the coefficient of static friction times the normal force. And so we're going to compare that with f cosine theta. So we'll plug in our 20 degrees first, or sorry, 20 newtons. So 20 cosine 30 degrees versus 0.8 times that 39 number. So that turns out to be 31.2. This turns out to be 17.3. So therefore, no movement. Our static friction force, we're going to have to overcome that 31.2 in this scenario. So the thing in which this is different than the problem that we did in class is that note that the normal force right here depends on the force. So I'm not always going to have the same normal force here. If I start pulling with 30 newtons on that rope, now I'm pulling 30 newtons up versus 20 newtons, that 30 is going to pull more up on the object than the 20 newtons was pulling up on the object, and so therefore the normal force is going to be a little bit lower, and therefore the friction force is going to be a little bit lower. So unfortunately that means I'm going to have to do this calculation right here. The free body diagram doesn't change, but some of these numbers do change. Well, the force right there does. So for 30 newtons along the rope, I still have the 5 times 9.8 minus, now I'm going to put 30 sine of 30, and this is 34. So if we look back over here, I'm going to plug that 34 now in for my static friction force maximum. So mu s times n is now 0.8 times 34, and that's 27.2. Notice the static friction force is a little bit lower than the 31 because when we're pulling more along this rope, like I said, that's going to ease a little bit of the weight. There's not as much, it's pulling opposite of the weight, so the normal force is not as strong. If I compare that with the 30 cosine 30, notice 30 instead of 20, I end up with 26.0. So unfortunately, 26.0 versus 27.2, still no movement. Okay? So at this point, it's really probably best to make ourselves a table, just because we're going to have to check 20, 30, 40, 50, 60. And you can type the formulas into your calculator and have it table these things for you. We're not going to go all the way up to 70. You'll actually find out where it's moving well before that. So plug in those first numbers. This was just the normal force that we calculated first off right there. Then the static friction force of 31.2, and the F cosine theta, the horizontal part of what we're pulling, is 17.3. So obviously right there, those two, no movement. We plug it in for 30, still you have 34 for the normal, 27.2, 26, we saw that still wasn't. Now, like I said, this is what we're comparing. If we plug it in for 40, and I'm not going to do those steps right here and then plug it in over there. I've already done that just to show you where the numbers kind of line up. The normal force is 29, the static friction force maximum is 23.2, and the horizontal component of the tension on the rope is 34.6. So when I'm comparing these two numbers, this is what's horizontal. If you look up there, the F cosine theta and the F. Alright, and finally we have a situation where F cosine theta, or F cosine 30, is more than the static friction force, which is awesome. That means that even though there was no movement there, yes, there is going to be movement here if we start pulling that with 40 newtons. And that trend just continues for 50. When I compare those two, we've got 19.2 versus 43.3. 60, we've got 15.2 versus 51, yes. And that's just going to continue all the way down the line. Alright, our second problem of 2 is kind of similar. We have an angle here, but instead of pulling this crate with a rope, we are pushing it, but we're pushing it up an incline. This incline has to be 50 degrees. So it is still a steel crate, still a steel loading dock, and we are still concerned with the 20, 30, 40, 50, so on and so forth. So what we're going to do first is draw our free body diagram. I'm going to accentuate that 50 degrees just so it's really, really obvious that we've got a ramp here. And let's walk through what we've got here. We've got weight going straight down towards the center of the earth. We are pushing it with, we'll just call that F once again. Friction is opposing our movement there to the left. And the normal force obviously is perpendicular to the surface. It's not going straight up, it's going perpendicular to that ramp. And if you remember on ramp problems, what we do is we set our X and Y axis to be slanted so that the X axis is along that ramp and the Y axis is perpendicular to it. It's really nice that way because then the normal force is right along the Y axis. I'm going to replace the weight with mg because that's normally what we do at this point. And turn that weight, which happens to be in the third quadrant, I'm going to put that down, break it down into its components. So we've got mg cosine theta and mg sine theta. If you remember, we've gone through the process of how to do this many times and why these are cosines and sines rather than the other way around. So you can look back in your notes if you're curious about that. So we'll now write Newton's second law in the x direction. So everything to the right is positive, everything to the left is negative. So we have F minus, there's a big F, the force which our physics crate pusher guy is pushing, minus little f, the friction force, and also minus mg sine theta. That's the part of the weight that is pulling it down the ramp. That equals mass times acceleration in the x direction. So we don't really know if there's any acceleration. That's really what the whole question is about. So fundamentally, we're comparing the force with which we're pushing it to these two other things combined. So since they're both subtracting, we can actually just sort of add those two up and see how do they compare with F. Before we can do that, though, we're going to write the Newton's second law. So it's normal, because it's positive, going up, minus mg cosine theta. It's actually pretty simple here in the y direction, is equal to mass times acceleration in the y direction. Since our object is not accelerating along the y-axis here, we're going to set that equal to 0, which is nice because that just tells us that the normal is mg times cosine theta. We'll actually throw some numbers in there. So 5 times 9.8 times the cosine of 50 degrees. And we get a normal force here of 31.5 newtons. So what's different about this problem from the last problem is that here our normal force doesn't depend on how hard we're pushing it, because we're pushing it along the x-axis. So that normal force is going to be 31.5 no matter where we are on the ramp, no matter how hard we are pushing this, assuming we're pushing it along the ramp entirely. Normal force is always 31.5, which is actually a significant time saver in this case. So what we're going to do is we're going to compare F versus the big F versus the friction force and the weight force, which is counteracting it. If you remember Fs maximum, the maximum static friction force we're going to get is mu times n. So we're going to combine these two and compare that with 20 first of all. So 0.8 times the 31.5 plus the 5 times 9.8 times the sine of 50, and this is the one that I get wrong. We'll fix it here in a second. So 37.5. I'm pretty sure that's not right. That's the maximum static friction force plus the mg sine theta. So 20 newtons, nope, not enough. 30, not enough. And let me check. Yeah, okay, that's not correct. The actual number, if you run it out, type the numbers in, it's 62.7. So 40 newtons, if I'm pushing with 40 newtons, that's still not going to overcome that 62.7. I put it in for 50 newtons. Nope, it's still not going to overcome the static friction force. Okay, I push it with 60 newtons. No, that's still not going to overcome. But with 70 newtons, finally, yes. And we're happy because we're able to finish this problem. It looks kind of complicated, but just drawing those free body diagrams and then just kind of tracing along, you're going to be able to get to a good answer. All right, thanks for watching. This was friction with rope and on a ramp.